recording for lecture number 2 for the composite materials class. Here we will start with the advantages of composites. We already talked about a little bit about this, but if you really compare uh, from a weight standpoint, see the difference. I mean, steel is about 7 to 8 times the weight of composites, and aluminum is almost double. But sometimes, since the strength of composites is much higher than aluminum, uh, so the weight savings is probably more like 60 to 70%. Thermal expansion also, composites are much lower in thermal expansion. The stiffness is much better than steel for the same weight. So strength is higher, fatigue resistance is higher. But if you look at the stiffness, strength, and fatigue resistance as a function of weight, composites are far better than any of these materials. One thing to note is that the strength of the fiber actually decreases with increasing diameter, or the strength actually goes up with decreasing diameter. And there is also another reason for this improved strength or improved uh, properties um, on an average. And the reason is that there is something called a critical flaw size for most of these brittle materials. So beyond that, it will fail in a catastrophic manner. But many of these fibers are smaller in size than the critical flaw size. So therefore, the probability of finding a critical flaw in a small fiber is very, very low. So therefore, you will have a very narrow band of strength properties of, say, if you took 1,000 fibers, they would all be narrowly bunched across one single average strength. And so from a population standpoint, this gives you much more uniform properties. And as I said, the strength actually decreases with strength increases with decreasing diameter. But when you increase the strength, there is a small problem. That is, how easy it is for you to wrap these fibers around a tooling or place them in a mold, etc. And that is based on what is called fiber flexibility. And this is related to elastic modulus and the moment of inertia given by that equation. So it's actually flexibility is equal to 1 over mr, and or it's also equal to 64 times 64 over elastic modulus times pi into d to the power 4. So the smaller the diameter, the more stiff the material becomes. The way you represent it is you represent the fiber diameter of different materials with a flexibility equal to that of a 25 micron diameter nylon fiber. So you can see that the stronger materials like carbon, silicon nitride, zirconia, alumina, silicon carbide, boron, etc. They are almost bunched along the same line, and they all have pretty high elastic modulus. So you can see that silicon carbide is probably the stiffer one compared to the diameter of the fiber. So the fiber spinning process, there are four basic variations of the fiber spinning process. First one is the wet spinning. and most of the carbon fibers, etc., are made by wet spinning. The other one is dry spinning. You can also melt a, um, a precursor and pull it through a set of dies. It's called melt spinning. Or you can also have a what is called a dry jet wet spinning. And all these basic variations are selected based on how well you can orient the chain of atoms in the fibers. What is the effect of stretching the fibers? What kind of a skin effect do you have in these fibers, and the draw ratio, etc. So typically a glass fiber is done by what is called a melt spinning process. You melt it in a furnace, and then it comes out through multiple dies with almost like 500 to 1000 holes, and it comes out. And as it comes out, it is cooled, and there is a collecting device, and then you just pull it and collect it across a mandrel or a spool. So these are the various forms of fibers. You can have a chopped strand mat, you can have continuous yarn, you can have woven fabric. And the two varieties of glass fibers are, the first one is the E glass and the S glass. You can go back and check what is the varieties of that. So E glass is the standard variety, and the S class is the variety used by the military applications and so on. So in the glass fibers, it's either done by melt spinning or what is called a sol gel process. So you dissolve it in a solvent, and then you pull out the material, and then you evaporate the solvent. And in this process, the fibers are drawn at a lower temperature compared to other ceramic fibers. So this is on the left hand side, you see the standard silica glass network. But in many cases, what you have to do is you have to modify this network by adding, say, sodium oxide, or a combination of sodium oxide and calcium oxide, to reduce the melting point of this silica glass network, so that it is much easier for you to pull these material through different sets of dies. This gives you an amorphous structure, but and most of the time with glass fibers, you will not have a crystalline structure. If it is crystalline, it becomes extremely brittle. In the case of boron fiber, it's a chemical process, and as it is pulled, and you could have a tungsten wire substrate around which the boron material is deposited, and then as it comes out, it is pulled onto a drum and spooled. This shows a picture of a boron fiber production facility where high volumes of boron fiber is made, and this shows you the uh, comparison of the uh, wire speed versus various boron fiber diameters. So if you pull it at a very slow speed, you can probably pull it at a much lower temperature. But if you pull it at much higher speeds, you have to pull it at higher temperatures. If you go beyond a certain temperature, then these fibers tend to become crystalline and are undesirable. So you want to have an amorphous boron fiber. So depending upon the temperature at which you are extruding it or you are pulling it, you can choose the right kind of wire speed. This shows the cross section of a boron fiber with a tungsten wire core. So the inside is a tungsten wire core, and the boron is uniformly deposited around it so that you get a perfectly circular fiber. Now, one thing to note here is this: 1 centimeter is 10 microns. So this is approximately, the whole fiber is approximately 100 microns or 1 millimeter or so. Compare that to carbon fibers. Carbon fibers are of the order of 5 microns or even lesser. It used to be about 10 microns, 7 to 10 microns, but now carbon fibers are made at a diameter of 5 microns or less. So this one shows the reaction zone around a boron fiber. So you have around the center, you have a reaction zone where you might have the boron reacting with the tungsten wire and forming tungsten boride of various stoichiometries. You might also have some silicon carbide formation around the fibers in around the boron structure. If you look at it at very high magnifications, you can see that the boron fibers have um, what is called a corn cob type of structure. And because when the boron is depositing around the fibers, they are not going to be depositing in uniformly. I mean, so first some part deposits and then more boron comes around it. So it tends to become a corn cob type of structure. Now, when you do that, when you deposit it, you're going to have different kinds of stresses around the fibers. So you are going to have some amount of residual stress across the transverse section of a boron fiber. In some cases, it is good, but in all cases, I mean, you try to reduce the residual stress as much as possible. So this shows you the fracture surface of a boron fiber. So you can see that it is pretty brittle and it shows radial cracks. So this is a radial crack from starting from the tungsten fibers, and tungsten fibers are not as ductile or flexible like boron, so the fracture will tend to start from that point and radiate out. Some of the advantages of boron fibers are that it has got pretty low density, approximately the same as that of aluminum, but it has um, but it has got a very high melting point. So, and it has got pretty low thermal expansion coefficient. So it's a good high temperature fiber reinforcement for different materials. So if you have, say, um, a metal matrix composite, you will tend to use boron fibers because it can take very high temperatures and it has got good and low thermal expansion coefficient, so that the material doesn't crack at that point because of the difference in uh, thermal expansion coefficient between the fibers and the matrix. Now coming to carbon fibers, carbon or graphite has a hexagonal close packed structure. So these are the different carbon atoms. So they tend to pack well and go around that. And this is a schematic of that. And it has a hexagonal layered structure, which we call AB structure. It is stacking so it is pretty strong in the linear direction, but it is pretty weak in this direction. So let me stop here and follow that after the next one.